this Q4 beam analysis type of meshing, the mesh was done by plotting the coordinates of the nodes by connecting it and make sure that it is 2 rows and 10 columns as shown in the figure. And the boundary conditions was applied, which is the fixed support is at the left side of the end of the beam, and the other end of the beam, which is the free end, is applied with the 2000 Newton of force. So when we run these simulations in the LISA software, LISA FEA software, the displacement at y-axis for the free end side of the beam, which is shown in the figure, it shows as blue color, dark blue color, which is the value is 0.0009115 with negative value, which means it's going to downward directions. And the lowest deflections or displacement is at the red color, which is at near closer to the fixed support of the beam. Then for the principal stress, the highest stress is 589.4 megapascal, which is at the side of the fixed support at the top of it, and it slowly distributes to the lower part, and the lowest sections of the stress is at the bottom of the left corner of the beam, which is near to the fixed support. When we substitute the phi2, we can get for 0.001 meter. That is the deflections. With the negative value, it means that it will be in downward directions. After calculating for the displacement at the free end, then the maximum principal stress was calculated by the equations given, which is mc over I. M is referring to the moment, and C is referring to the centroid axis, and I is referring to the moment of inertia. So after calculating it, it is found that the maximum principal stress obtained is 600.06 megapascal. In this table, it shows the numerical comparisons of CST and Q4 element models and element defects. So for the four of this meshing, the number of nodes are the same, which is 33, and the number of degree of freedom also the same, which is 66. The only differ for this different type of meshings is the free end displacement and the principal stress. For the free end displacement, the percentage difference is the smallest at the Q4 meshing, which is about 8.85% as compared to the classical beam theory, which is obtained negative 0.001 meter. So it is closer to the classical beam theory. And the CST has higher percentage difference compared to Q4 because of its stiffness. CST has much stiffer meshing than Q4, so this is why it does not displace much, and it results for larger percentage of difference. And for the principal stress, also the same. Q4 have the lowest percentage difference, which is 1.77. It is compared to the classical beam theory, which is obtained on the previous, which is 600.06 megapascal. And as to compare with the FEA LISA software, the principal stress obtained is 589 and 89.4 megapascal, so it is quite close to each other. So that is why the percentage difference is small, and the CST have the larger percentage difference. As these relationships actually we can see from the free end displacement, which is that if the free end displacement getting closer to the classical beam theory, the principal stress also getting closer to the estimated classical beam theory. So in this case, it shows that the Q4 has better and more closer to the classical beam theory, which is the percentage difference is quite small. And for the CST, the different type of CST has different type of performance, which is different free end displacement and principal stress. Although it has the same 2 rows and 10 columns of meshing, but due to the different type of form, it produces different type of results. And as to compare between the CST only, it can be seen that the CST type 3 is the closest to the classical beam theory, because the percentage difference is quite smaller compared to the other two CST with type 1 and type 2, and the largest difference is at CST type 2 for the free end displacement, but for principal stress, the largest difference results is from the type 1 CST. The reason why it is meshed as such is because the aim is to have the transitions from the smaller quadrilateral to the larger quadrilaterals. So that is why it is used the triangular elements at the center of the structure. So these transitions is necessary because intermediate nodes along element edges are inconsistent with the energy formulations of the CST equations. From the material selections, the FEA result shows some of the stresses, but the stress that we pick is von Mises stress because it is a ductile materials. Von Mises stress is more suitable for ductile materials. And from the figure shown, for the von Mises stress, it shows that the highest stress is at the right side of the beam, because the force is applied at that side. For this brittle material, the stress that I select is the principal stress because it is brittle material. So the maximum principal stress is at the top, at the bottom right corner of the structure, which is 2.46 exponent 4 Pascal. As a comparison between this ductile material and brittle material, it shows that the highest stress occur can be at the ductile material and the slightly lowest high stress occur is at the brittle material.